the biggest one in the fixed side and one of the major one in the mobile market. We are a convergent operator coming from the monopoly, so the incumbent one. And we have around, let's say, in the consumer side, the 20 million customers that are receiving our services, both in the fixed and mobile and in the TV side, right? So the telecommunication market in Italy, I think, is one of the most aggressive in Europe. In the mobile side, we have 4 infrastructure operators and many mobile virtual operators. And in the fixed side, there are some global operators national-wide, but also we have a lot of local niche players that are competing with the Telecom Italia. So our offering, you know, in the mobile is basically a service based on LTE, so 4G evolving to 5G, and in the fixed side we provide fiber to the cabinet, and we are going to provide fiber to the home more aggressive in the next years. So the competition is very, very strong compared to the rest of Europe, and our average revenue per user is decreasing every year because of this competition. So it's very important for us on the business side to keep the customer loyal. Okay, in this moment, I would say that the telecommunications are quite similar to a commodity. It's very easy to change an operator, and every provider looks similar to the other. So it's very important to, let's say, keep the customer loyal with more additional services, also with the quality of the service which is higher than the competition. So that's why today we are submitting a proposal for a data competition in the fixed side for the churn, because this phenomenon is increasing in Italy, and it's very important for us to keep an eye on how we can use the technology like artificial intelligence, machine learning to improve our intelligence in targeting the customer which are likely to switch operator. Okay, so just one brief introduction from the market side. Now this chart by Gartner tells us how in the industry is very important to use artificial intelligence in the real business. It's not anymore an academic topic. There is really a convergence of phenomenon which can allow keeping the momentum to put artificial intelligence in production in the industry. So you know that the computing is power is incredible now. The storage is very cheap, and the artificial intelligence algorithms can be plugged into production very easily. So mainly in the industry, just for you that probably most of you come from the academic background, we see one of the few opportunities to transform what the research institution and the university are rolling out in terms of research into production with very concrete results, mainly in cost reduction. So we can have algorithms for predictive maintenance, for example, on the network side. In the revenues, because if we reduce the SARN or improve the upsell on the targeted on the customer, we can gain revenues, extra revenues. And in the customer experience, because if we understand better the customer, you can better handle the customer journey through all our touch points. So it's very important artificial intelligence goes in production quite soon. Okay, we have started a project in Telecom Italia a couple of years ago, and two of my colleagues here, Andrea and Dario, are part of the team that was formed to bring the machine learning inside Telecom Italia, together with new investment in technology, of course. Just to tell you and to have an idea, in Telecom Italia at the moment, only talking about structured data. We have 4 petabytes of data into one single platform to be worked out. But introducing also non-structured data like emails or video, audio that comes from the call center, we can have an incredible amount of information in future. So it's very important for us to keep attention to big data and to the artificial intelligence and machine learning evolution for exploiting it into the business. So let's talk a bit about the churn. Okay, the churn rate, it's a phenomenon which is quite important. It's approximately 23% of customer every year churn operator in our from our network. So 1 out of 4 is changing operator every year, and it is typically replaced by a new customer. And the new customer has an acquisition cost. Normally, the acquisition cost of a new customer in terms of advertising, agents, shops, etc., is approximately €250 per single customer. And this tells us that if a customer does not stay with us at least 8 months, then we are getting lost. So it's very important that we keep the existing customer rather than replacing them with a new one, right? Because in this operation, we can, our price is lower, so we lose margins, we lose revenues, because the old customer pays more than new customer. And at the same time, the new customer is if this customer does not have a good experience in entering in our world, like delivery time, problems of the early installation, etc., there is a high risk that it can switch again. Okay. Why we have this scenario? As I told before, in Italia there are a number of operators in the fixed side. There is mainly one network built by Telecom Italia, but according to the regulation, everybody can access our network, even if they do not have the last mile and they do not have their own infrastructure. So it's very likely the customer can get an offer also from an operator which is not infrastructure or does not own the network. So the Telecom Italia market, it's decreasing because, of course, we are attacked by many of these players. And the competition is also different territory by territory. So one dimension to consider is also the geography, right? Because there are areas where we are not yet providing the fiber, or there are areas where we can sell, we do not have shops, or we do not have good sales. So as you can see in the map, the churn rate can be differentiated region by region, town by town. So the geography is an important variable. So since the time is not too much, I will just go directly to the competition to give you a brief introduction of what is this competition. Okay. So the objective we ask to the participant is to produce a classic predictive model for classifying the churn probability for each single user. And in doing this, of course, we will look at the most exciting work, the most accurate model measured out of the algorithm. But also, we will look at the relation that we ask to provide, about 10 pages relation, where the candidate should tell us, to the commission, together with the university, what are the main findings of this analysis? What is the methodology? What are the variables that were introduced in the algorithm? Any idea in clustering the customers? Okay, in how to address specific customer clusters, even niche clusters. Okay, because of course, traditionally the marketing clusterizes the customer in very big clusters of small, medium, large, whatever. But we all know that once you have a lot of variables, you can cluster the customer with a lot of dimensions. Okay. We expect that this competition can be description, subscription to the competition can be done by a single person or teams up to 3 persons. Okay, so you will find a registration form where you can form a team of 1, 2, or 3 persons. We have decided, together with the university, to provide prizes for 2 winners. So the winners will receive an award in money, I guess, no? And the choice of the winner will be based in a mixed commission with the team and the members of the university, where we will look, as I told you before, mainly to traditional performance KPI for accuracy of the algorithm provided, like the ROC curve or accuracy of the algorithm, but also to the best insight that will be provided by the participant. The timing of the competition basically is today we are launching the competition, and we will advertise. I hope also some of the people here can advertise this competition elsewhere in other members, university students, communities, where we can get interest in participate to this competition. And we expect that by 2nd of October, the participant can deliver the final results in terms of algorithm and paper. And basically, the idea is to analyze all the papers and results and choose the best works for being interviewed, for exposing personally what could be the way they build these models, and choose the final winners by end of October. This is the idea. In terms of registration, basically we have on the cladag site, there is a form, there is a section of the site which is called data science competition, I believe. And in this form, the participant can subscribe. There will be some data that will be asked for the participants in order to access the download page where they can receive all the data set, the instructions, the daily instruction to participate to the work. So in this site you can have the data set, the metadata describing the data set, and the instruction to participate. The data set mainly, it's real data from Telecom Italia, based on real users. So you have 9 months of data with on a sample of approximately 10,000 customers that are, of course, masked. So you have a pseudonymization of the ID of the customer, plus a set of almost 200 variables describing this user on a range of dimensions. So usage, so how many data, how many voice calls, duration of the calls, etc. Anagraphic, so where they live, age, sex, gender, and so on. How much they spend with us every month, and a lot of other dimensions, also including quality, call center activities with us, trouble ticketing. So you have a view of the customer in terms of his profile, of course, in terms of average the KPI, based on a monthly basis. So based on this, we provide the test data set also to train, to test the final algorithm in order to provide the result to us. We will retain the variable about who really churned in the last period in order to check if the algorithm has the right performance. And we will rank all the received proposals in terms of results. We also ask eventually to the candidates to analyze if they can extend the team data with other external data, open data that can come from the National Statistics Institute, for example, or other open data provided by regions or other public database or private database to enrich the data set to improve the algorithm and the insight. So this is up to the participant. This can be quite important because, of course, you can enrich the data in crossing also other information. For example, an average salary of one family in one region or other information can come from national public statistics. Okay. So that's it. So I think it's quite interesting for us as a let's say private company to really stay close to the university and to the research, because really one of the areas where we can keep benefit of the work done in the university is artificial intelligence, because it's something that where the idea, together with the people like us that have a lot of data, can really fastly bring to concrete results. So that's, I think, something we hope we can repeat in the following year. This is the first year. So all the result of this experience will help us to design and improve for the future. And please participate as you can to this competition. We will be very happy to see what the students, your colleagues can do. And thank you very much.
Briefly, only two aspects. The participants have to use R or Python code, and the prize is in money, 2,000 euro for the first prize and 1,000 euro for the second prize. Okay, thank you.
Okay, so before okay, so before starting the session, we have two announcements. The first is that all the session in the rest of the morning are postponed of by 20 minutes.
Yes.
So there's that are involved in the invited session after this plenary. I have to consider 20 minutes later. And the second...
Please speak. No, it's just to announce the composition of the new scientific and organizing committee of cladag. And after the election, we have Francesca Greselin from Milan, Leonardo Grilli from Florence, Giovanni Camillo Porzio from Cassino, and the vice president, the president-elect is Cinzia Viroli from Bologna. And after the modification of our bylaw, and we have that Roberto Rocci, as past president, stay in the committee, in the board, and Francesco Mola as president. Good luck.
Okay, so, and I try to introduce the next keynote speaker is Bettina Grun, as she deserves. Bettina, so I would say that our discipline is, the three pillars of our discipline are methods, applications and software. And looking at the CV of Bettina, we can appreciate that she has produced very interesting papers, and she has given very relevant talks in many conferences all around the world, touching these three aspects. So, in my opinion, but I think that can be shared with almost all of you, a statistician that has the ability to touch all these three aspects is a complete profile of a statistician. She is a professor in Austria at the Linz University. She has published tens of papers of most relevant, prestigious journal in our domain, and she has authored and co-authored 7 of the most used and useful package in R. So, Bettina, the floor is yours.
Thank you very much for the kind introduction. And I would like to thank the scientific committee for organizing, for inviting me to speak here. And today I would like to present some work I've been doing together with Silvia Frühwirth-Schnatter and Gertraud Malsina-Valli, and it's on Bayesian model-based clustering. And what we've been doing was investigating how can we do a good prior specification in order to induce the properties we're interested in our Bayesian mixture model. So the idea behind model-based clustering is we have a mixture model and we use it to obtain a clustering where each group is assumed to have its own distribution. And in this talk, I'll more or less only focus on the mixture of Gaussian distributions. So we assume we have a finite mixture of Gaussian distributions, and to fix notations, we have the component weights denoted by eta, and then we have the component distributions, which are all normal distributions, and they are only differing with respect to the mean values and the variance-covariance matrices. And if you think about model-based clustering, and if you go to conferences like cladag or others focusing on clustering, classification, there are issues which sort of come up now and then, and you think those haven't been solved yet to a satisfactorily manner. And some of the issues which come up, one is always like, how do we select the suitable number of components, or how do we select the suitable number of clusters in for our clustering problem? If we have this range of variables, can we distinguish between cluster-relevant variables, and can we omit some of the variables from our model to get it more parsimonious, more simple to interpret, get better results, and so on and so forth? And often also, if the starting point is the mixture of normals, is this already it, or do we think we need something more flexible for the cluster distribution? So what happens if we have non-normal shapes for our clusters? So these are these issues which come up, and people try to tackle them with different approaches. And our approach is to look at these problems from a Bayesian perspective and think, how can we solve these issues using suitable prior specifications? Because this is what we complement our likelihood model with. We have the prior specification, and the priors sort of also allow us to smooth and regularize the likelihood. So in some sense, we have both. If we look at the posterior distribution, it has two components. It has the likelihood of the model, but it also includes the information from the prior we have been using. And some of the issues we see in maximum likelihood estimation can sort of get smaller, or you can get rid of using good prior specifications. And the example I want to give for that is, if you look at the likelihood of a Gaussian mixture model, you think Gaussian mixture models is sort of the most basic model we could use. And still, if you think about the likelihood, it's pretty complicated and has a lot of issues. So it's known that it's potentially multimodal. So you have a global mode, but there might also be minor modes. How do you deal with this? And you also know it's unbounded. So if you have singular variance-covariance matrices, you have infinite likelihoods, and this is something which is sort of not nice if you do maximum likelihood estimation. And also in a context, if you think about overfitting mixtures, so if you have more components in your mixture model than you really need, then the likelihood has two different possibilities to deal with these additional components which are not needed. So if there's a component which you don't need, you could either leave it empty, and then sort of you cannot decide on what should be the component-specific parameters, because what do you care if it's an empty component? Or the other way around, you could just duplicate two components. So you have two components with the same set of parameters, and the identifiability issue you have then is that the component weights, like it's only the sum of the two component weights which is identifiable, but it's unclear how you could assign proper weights to one or the others. But it's the likelihood can just incorporate both of these states and reflects it. And the idea is with priors, the posterior can sort of be guided to focus on a single mode, get rid of spurious modes, and also in this overfitting case, focus on one or the other strategy to deal with additional components which are not needed. And one example from the literature, pretty old one, is the so-called Kiefer-Wolfowitz example, which tries to indicate that having these sort of spurious modes, it's coming up sort of in any arbitrary data set of arbitrary size. And the example they came up with is a very, very simple one. So you have a mixture of two univariate normals, and you assume that for this two-component mixture, the mean is even the same. So you're fixing the mean, and you also assume that you know the variance of one of the components, and what you don't know is the variance of the second component. And you also assume, in the subsequent example, we assume that we know that the component weight, we fix it at 0.2. So the only two parameters which are unknown is the mean and the variance of the second component. And still, if you think, you could have spurious modes, because once you put the mean to the value of one of the observations, you can get the variance down to 0 and have sort of an unbounded likelihood value for that observation. And this is still possible in this setting where you sort of freely can vary one of the variances. So you're estimating one of the means, and you can go with one variance to 0, you get this problem. So to visualize it, we simulated a small data set with 20 observations with the mean 0 and the variance 4. So the true value is for the standard deviation 2 and for the mean 0. And each of these 20 observations sort of can cause a spurious mode in the likelihood. And if we look at what the likelihood looks like, so if you look at it from this perspective, so you have on the plane, it's the mean and standard deviation. So you think, okay, there is sort of a mode at 0 for the mean and 2 for sigma. But then behind that mode, there's something weird happening. And something where even higher values for the likelihood can be obtained. And if you turn it around and look at it on the log sigma scale, so now you're looking at the same 3D plot, but from the perspective of you have very, very small values for the standard deviation. And then you see these spikes. And these are due to, okay, if mu is equal to exactly one observation and you go with the variance to 0, you get huge values for the log likelihood. And this is what the log likelihood looks like. And if you do maximum likelihood estimation, you have to deal with that kind of thing. And you need to find the maximum in that thing. And obviously, there is sort of a local maximum at the point which would be close to the true one, but there are all these additional spurious ones, edges, ridges, ridge lines, and so on and so forth. And if you think of, okay, if I now impose a certain prior, getting rid of, a priori, I know I'm not interested in a mixture which has these very, very small variance values. If I use such a prior, like an inverse gamma prior for the variance. And then I look at the posterior. So this sort of the combination of the likelihood and which has the spurious modes, but the prior saying these values are sort of impossible, in combination gives you a posterior, which is sort of the global mode is the thing you're interested in, that's fine. And in some sense, this is the solution you're interested in. You're not interested in a solution where the variance goes to 0. This, from a priori, you know this is not a good description for your data. So if we want to do Bayesian mixture modeling, how can we proceed? If you want to get the posterior, normally the easiest is if you can use a conjugate prior, then you get the posterior being from the same parametric family, and you have closed form solutions. This is not possible in the mixture case because there is no natural conjugate prior, and the use of mixture models has only started with the MCMC methods being introduced and being available. And there has been a very influential paper by Diebold and Robert in the 90s, where they've shown how can we use sort of Gibbs sampling strategies for fitting a mixture model. And the idea is sort of similar to what you're doing in the EM algorithm. You just do data augmentation, and the unobserved component memberships of your observations are just part of the sampling scheme. So if you do this kind of data augmentation, then the approximation of the posterior sort of gets rather straightforward, or at least you can reuse a lot of things which are available already. So it boils down to using things which are already available in Bayesian estimation. And essentially what you end up with is 3 steps where, like the first one is generic, regardless of what kind of mixture model you have or what kind of component distributions you're using. You just need to sort of classify the observations. So you're drawing from the posterior probability that an observation Y comes from a component G. And this is something you would need to calculate in the E step of the EM algorithm, and here you do the calculations and then you draw from the multinomial, and then you have hard assignments of observations to the components. So you get a partition, and conditional on the partition you continue in the next step. So once you have partitioned your data, you sort of have just the component distributions for subsets of your data sets. And this is, you fall back to, if you're interested in fitting a mixture of normals, at that point, you need to fit the normal distribution. And you can reuse whatever is available for fitting that kind of model in Bayesian estimation. And you need to sample for the component weights. And often people also have hierarchical priors, then you would need the additional step of sampling the hyperparameters. So this would be a very, very generic sampling scheme for how do you do Bayesian estimation in mixture modeling. If we now want to specify a prior, we have to make a few decisions, and when we were thinking about how could we specify the prior, the idea was also we are coming from a model-based clustering context where a priori you do not differentiate between the components. So you want to have priors which are sort of exchangeable or symmetric in the components. So there might be other applications for mixture models where you think you know certain roles for your components, and then you would have sort of an asymmetric prior. But in this context, you assume you neither know the number of components you have, and you think a priori they are sort of exchangeable. And the easiest thing is to do if I have the set of parameters. So the set of parameters I need to specify priors for is the component weights, the means for the normal distributions, and the variance covariances for the normal distributions. And normally it's easiest a priori to assume those 3 sets of parameters are a priori independent. So this joint distribution factorizes into a product. And then you could even say for all of the component distributions, I also assume it's a product over the components. So we assume they're symmetric. And what has often been discussed also in Bayesian estimation for mixture models, what has been also perceived as sort of a disadvantage is that you need to use proper priors for the component-specific parameters. Because if you think about calculating the posterior, you could also get it by summing over all possible partitions, and which means there are always partitions where some components might stay empty. And if there are no observations assigned, the posterior is equal to the prior, meaning if you have an improper prior, you'd also end up with an improper posterior. So what you need to do is you need to specify a proper prior for your component-specific parameters. So years ago, there have been some ideas of doing other strategies, like only including partitions which assign observations to all of the components and things like that. But people have more opted for the option, okay, it needs to be proper, and then we can move on. But what's often done to ease also the sampling step is use sort of conditionally conjugate priors, where you end up with a sampling scheme where each of the steps are available in closed form. And if you're unsure about certain parameters, you can always try to have hierarchical parameters. And in some sense, hierarchical priors, for example, would also allow to share information between components. Good. So if we want to do sparse modeling, how can we use priors for mixtures of normals? And in one hand, we can use it for the prior on the weights. And the idea is if we're in an overfitting mixture, can we sort of use a sparse version of the prior, which induces some components to stay empty, and in this way give us the possibility to estimate the number of filled components, and in some sense, in one go, try to estimate the suitable number of components to reflect the mixture. And the other is the prior on the component means, which would allow us to distinguish between relevant and irrelevant variables. Can we use suitable prior specifications on these two sets of parameters, which would help us to solve sort of these first two issues which are open in model-based clustering. So the prior on the weights, if you want to stay within this conjugate, conditionally conjugate setting, the idea would be to use a Dirichlet distribution because it's sort of the conjugate to the multinomial. And if you have this symmetric prior, you only need to have one parameter, which is denoted here by E0, and it's the same for all from E1 to EK. Which means if you have this symmetric one, a priori all of the components should be the same. This means that the mean a priori of your component weights is the same for each of the components, and it's 1/k. So a priori you sort of impose that each of the components on average have the same size. If you can exchange it, that's something which needs to be. So the only thing you decide on with your E0 parameter is the variance. So how much weight do you give to this equally weighted solution to alternatives? And if you look at, for example, draws, this is drawing from the Dirichlet distribution with different number of parameters in 3 dimensions, sort of. If E0 is high, so for 1,000, you get all of the observations are close to the midpoint. You put a high weight on a priori knowing that each of the 3 components are filled and each have the size 1/k. And if you now decrease your E0 value, then there is sort of a point where it's equal to 1, which sort of decides, do you concentrate on the interior of the simplex, or do you put sort of weight outside? So you have first, it's shaped like that, then you get the uniform for E0 equals 1, and then it gets sort of into a cup shape, putting more mass on the edges. of the simplex. So E not equals 1 is the uniform distribution. You think each of the combinations has equal weights. And afterwards, if you're getting smaller than 1, you're putting weight on the edges, assuming that you have components which are sort of have a weight of 0 if you're on the edge. And what has been done usually is you would think the uniform distribution seems sort of uncontroversial. At least if you think about map estimation, then the a posteriori mode is the same as the likelihood mode, and they're just the same. And if you look at the posterior updates in the Gibbs sampling step, if you draw the weights, what you get is in each of the posterior parameters, it's the sum of the number of observations you have assigned to that component plus your a priori value. And this means you can also interpret k times E naught as sort of an a priori sample size you're adding. So you could also think what you're doing if you look at the mean is the posterior mean reflects sort of a sample of the data you have observed and the prior sample, which has then size n plus k times E naught, where from your prior sample you have just added E naught observation to each of the components. And the posterior mean is sort of pulled towards a solution where each group has the same number of observations. So if you would assume the number of components is known, so you want to fit a mixture with 2 components, and you know there'll be strong evidence for these 2 groups, more or less the results won't vary much depending on how you choose E naught, because if you have a large sample size, you only have the sum, and you would always assume E naught is small compared to what your sample size is. So this might be rather uninfluential. But if you have model uncertainty and you want to estimate the number of components, then selecting a suitable value for the Dirichlet parameter gets important. And it depends on what your strategy is for model selection. So depending on how you want to proceed to select the suitable model, you would need to choose a different value for this parameter, because one tends to fill all of the components, other values tend to empty components. And if you think about the overfitting mixtures, we have said that the likelihood has these 2 different ways of dealing with overfitting, either having empty components or duplicated components. So if you have a component you don't need, the likelihood has modes for both situations, either having 1 empty or 1 duplicated. And this is multimodality, and it's the prior which decides on where will the posterior focus on which of these 2 modes. So this is something which stays regardless of sample size. So even if sample size goes to infinity, it's the prior in the overfitting case which will decide on which of the modes the posterior will focus on. And there is a result by Rousseau and Mengersen they had in GRSSB where they formally proved what happens asymptotically to the posterior. It's the likelihood being completely indifferent regardless of sample size, so it's the prior which will always overwhelm and contain the information where the posterior should focus on, and it's you have sort of threshold point for your value of the Dirichlet. If it's below d half, where d is the number of parameters for your component distributions, then you will focus on that part where you leave components empty. If you're above that threshold, then the posterior will focus on duplicating components. So there are these results. And this also has an impact in finite sample applications. So if you now think about the model selection approaches you're interested in, if you want to do marginal likelihoods or reversible jump, you might rather want to have something where if you have k components, all of them should be filled. So you want the model to use all of the flexibility you're offering, which would mean in such a setting, you want to select large values for your Dirichlet parameter, ensuring that all components will be filled, and you're using the flexibility of the model when you're comparing then different models, asking yourself, should you add this additional layer of complexity, yes or not? And the alternative is you could select a large value for the number of components, but a small value for the Dirichlet parameter, and then you get sort of a random variable of the number of filled components. And you can use the posterior distribution of that random variable to select a suitable number of components. So you could look at, for example, the mode. What's the most frequently number of filled components you're observing in your MCMC chain? And you can use this as an estimate for a suitable number of components. And the advantage of this second approach is you just fit it once with a large number of components, and you're getting to a solution with the suitable number of components without refitting the same model with a different number of components. So if we think about the prior on the component means, so the conjugate prior for the means would again be the normal distribution, and we have closed form solutions then for the Gibbs sampling step. And what we have is that because we need to use proper prior, we'll get sort of the posterior means being pulled towards the prior mean to a certain extent, just what we want. But that's the usual setup, and there have also been suggestions on how to select these prior parameters. So Sylvia Richardson has this paper with Peter Green in Juris SSB, and Stevens did the multivariate extension for what would be sort of data-driven starting points for these parameters, using the midpoint for the prior mean and sort of a very generous variance-covariance structure using the range squared for the variance-covariance matrix. But if we want to now use this prior specification to decide between relevant or irrelevant variables, we can also think about how can we change that prior on the component means to have this desired behavior. And normally, why do people want to get rid of cluster irrelevant variables? There are normally two reasons given. One is that they mask true cluster structure. So if you just have too many variables, the problem gets harder than it needs to be, and sort of getting rid of things which might confuse allows the algorithm to focus on a specific good cluster solution. And also, if you estimate k different component means, if you don't need it, you have this too much heterogeneity in your model, you're wasting parameters, which means normally you're increasing the inaccuracy of your estimates. So how could you proceed in getting rid of irrelevant variables? One is stepwise approaches or stochastic model search. That's one avenue, and we try to follow the second avenue using sort of shrinkage priors on the component means, where you try to decide on should all the component means be the same for one variable over all components, or should they differ? And in some sense, this is using shrinkage priors similar to what you're doing in a regression setting, where you want to decide on should a coefficient be equal to 0, or should it differ from 0, using this kind of prior setting. And here, you're not deciding shrinking, are you shrinking towards 0, but are you shrinking towards the common mean overall components? But otherwise, what we do is we're sort of borrowing insights from the regression case to come up with suitable shrinkage priors. And what we considered were scale mixtures of normals. So you still impose a normal distribution on the mean, but then you have an additional distribution on the scale, which sort of gives it the possibility also to have heavier tails. And this hierarchical specification is nice for estimation in MCMC sampling. And members of that scale mixtures, I think the most well-known might be the lasso, which is very frequently used in the regression setting. This is where the scale distribution is an exponential, the exponential being a sort of a special case of the gamma distribution. You can just use any kind of gamma distribution, and then you're in this normal gamma prior setting. And this is the one we were pursuing in our approach to distinguish between cluster relevant and irrelevant variables. So what you have is you have the component means following a normal distribution, where you have the mean, where you shrink to, and then you have this product between the variance you have specified times this scaling or shrinkage factor lambda, which follows this gamma distribution. So a priori it either has small values or very high values, and the shrinkage factor will tell you if I'm shrinking all together, all of the component means will be sort of have the value B not J, and if lambda is large, we have differences between the components. So the lambda sort of informs us, are we shrinking them together? Is this a cluster relevant variable? Yes or no? This information will be contained in the posterior distribution of our shrinkage factor. And for illustration, what do these priors look like on our means? You have the blue line, that's the normal prior, which sort of would also reflect a ridge penalty. Then you have the red line with nu equals 1, which is the lasso. And what we were considering is the black line with nu equals 1/2, which sort of even puts more mass around 0 and has heavier tails than the lasso. But this is sort of, if you look at the green, red, black line, that's the range you get with the normal gamma price. So what you see, if you have nu equals 1, you already have this edge at 0. It's a non-differential point, and you get more extreme if you make it even smaller. So you want to focus on small values for nu if you want to do this kind of variable selection. If you have now our price specified, we know how to estimate. What's left is sort of model identification, because we've said the likelihood is invariant to the labeling of the components. We've used symmetric priors, which means the posterior is also symmetric, and we have the label switching issue we need to solve. So if we are interested in component-specific parameters, we need to get rid of the label switching first, sort of focus on one of the permutation modes in the posterior and report with respect to that. And there's a huge stream of literature looking into how could we solve the label switching problem. And we've come up with yet another option, which we thought is very interesting to pursue in this context of model-based clustering. And in the model-based clustering, you would hope that the component-specific parameters differ between the components, at least with respect to some of the parameters, and often we would think already the mean parameters should allow us to differentiate between the different components. And what we looked at is using a label invariant representation. So we looked at the component-specific parameters in the point process representation, and then used normal clustering strategies to cluster the component-specific parameters, or a subset, like, for example, the means, which differ, where the means of the variables where the components differ, cluster there, and then look at how many of the draws allowed for a unique relabeling, and only retain those in subsequent steps, because experience has shown that if this unique relabeling rate is small, this normally is also a sign of overfitting, because you're coming in an area where you have duplicated components, where two components have two close posterior distributions for the component-specific parameters, so you can't distinguish between the two. This is an indication that you have more components than you really want to have a good clustering solution. So in some sense, this is very specific to model-based clustering, and it also gives you a hint how useful will this be to distinguish between the clusters you're identifying. And the modeling strategy, now if we think about we want to have a sparse prior on the weights, is to use a large value for k, but a small value for the Dirichlet parameter, and then hope for sort of unfilled components during MCMC sampling and use this as for estimating the number of components. And you can either use a small and fixed value, but we also investigated using hyperprior on the Dirichlet parameter following a gamma distribution, and we used for the component means the gamma distribution with both being 1/2, so the mean is 1, but focusing sort of having lots of mass around 0, having a lot of shrinkage, or heavy tails to decide between the two sets in a distinct way. And what we found out in combination between the two, if you also want to shrink, then you need to be more decisive in the weight distribution. So then it's sometimes easier to, like if you add more flexibility, it's harder for the posterior to focus on interesting modes. So if you want to have the flexibility to do variable selection, often it's better to then say very small values for E0. And we looked at a simulation to apply that method. So an easy setup with 4 components, 4 variables, but only 2 are cluster generating and 2 are sort of noisy variables where we want to learn that they're not containing any information about the clustering, and they could be shrunken together to have a common mean value. All of the groups had the same size, they all had the same variance covariances matrices, even though we didn't use that information during sampling. We estimated different variance covariance matrices for all of those groups. We had 1,000 observations, and we used 10 different data sets to sort of not get stuck with a single data set having some peculiar characteristics. And then we drew 10,000 draws after 2,000 burn in, and we summarized the results. So on the one hand, we wanted to look at the case where you would know that there are 4 groups. So that's sort of the oracle situation. If you know there are 4 groups and you're estimating it, and you have sort of a hierarchical prior on the Dirichlet parameter, where would be the mean, then, okay, if there are 4 groups and you have only 4, it fills all of these 4, then this is the number of draws where 4 components were filled, so you never had less than 4 components filled. That was the unique, so we didn't have any problems with the unique labeling. That's the misclassification rate, and that's the mean squared error when estimating the mean. So this would be the oracle situation where you think, if I would know, and now if we want to estimate the number of components during the same, so we used 15 for the number of components, and then you see if you learn the Dirichlet parameter, it's a lot smaller. So you have this combination, small Dirichlet parameter, large k, and still we have the most often filled number of components is 4. In fact, it's 9,709, and then there are a few draws where there'll be presumably only more. So it never empties, it never combines clusters together. But those 9,709, there was, when we did the model identification, we had no issues with relabeling, and it's essentially has the same quality of the solution if you look at misclassification rate and the mean squared error. And you have, if you increase the number of components from 15 to 30, then E0, the estimate value, gets even smaller, but otherwise the results are very, very similar. So you see this is a combination of two parameters, k and the Dirichlet parameter, and if you increase k and you make E naught then smaller, you can sort of estimate the number of components from the number of filled components. And now we looked also at this normal gamma prior, trying to, in the same run, also get results for the identifying the cluster relevant variables. And again, we have this situation where we have k equals 4, so it's sort of known. And what you observe is you get a more accurate estimation of your means. So it's because you can learn that for two variables, they're more or less the same, you get more accurate, there's less uncertainty in estimating that. So this is where the impact of the normal gamma prior is, it gives you sort of less uncertainty in estimating the mean values. But otherwise, it sort of works in the same way. If you increase k, you need to sort of reduce the Dirichlet parameter, and then you can estimate the number of filled components, and you get good results with respect to misclassification rate. Good. What do the trace plots look like? This is the number of observations assigned to the different components. So we started with having all of the k components filled at the beginning, and then it's quickly emptying those it doesn't need, and then you get to a steady state where some are just empty all the time, and otherwise it's sort of having these 4 components filled. And this is the posterior for the lambda parameters, where we should learn if they are small. So 3 and 4 are irrelevant, so the posterior distribution puts most of the mass close to 0. Whereas for the other setting, where they should differ between the components, lambda is much larger. So this posterior can tell us which are relevant, which are irrelevant. Good, so this is the distinction having component means and the cluster weights. And the next thing we were looking at is, if we're now in this mixture of normal setting, what's often seen is the number of components is higher than the number of clusters you're really interested in, because you're using several components to approximate one cluster. And there has been discussions on how should you specify. You could also say maybe the component distributions should reflect your prototypical cluster shape, and that might not be a Gaussian, then maybe you shouldn't fit a mixture of normals anyway. But you could also think mixtures of normals as a semi-parametric tool to approximate any kind of distribution. And in that sense, you could think, okay, I want to use now a component distribution which is a mixture of normals. So I get a mixture model which sort of has 2 hierarchies. You have the upper level where you have your mixture, and you have the cluster distribution, and each of the cluster distributions is a mixture of normals. And you have several subcomponents which again together form a cluster. So in some sense, this is a good way out to be flexible in what kind of cluster distributions can you approximate, and you're still within the mixture of Gaussian setting. So this is the advantage. If you think about using semi-parametric approximation for your cluster distributions, you don't really need to know a priori what cluster shapes you have, and you don't need to specify a specific parametric distribution for the clusters. This is an alternative avenue which has been pursued, in particular if you're saying, okay, maybe I have a heavier tailed distribution, I have skewed distributions. So Jeff McLachlan has been working in that area. Sylvia has also done some work in Bayesian estimation in that context. But if you think about staying with the Gaussian, at least the estimation step will more or less stay the same, so you can reuse everything and you don't need to develop new Bayesian estimation tools for whatever parametric distribution you're interested in for your component or cluster distributions. But the problem is, if you have this mixture of Gaussian mixture setting in these 2 hierarchies, is that the likelihood, again, is sort of invariant to reordering. So the likelihood doesn't know which subcomponents should be put together to form a cluster. And you again need to impose something to get identifiability, and in particular in the maximum likelihood setting, there were either constraints imposed to say, okay, if you're within a component, you have to share certain similarities, or there have been post-processing strategies proposed where say, okay, you first use mixtures of normals to approximate your density distribution of interest, and then you do, for example, some merging steps to form, like put together some of the subcomponents to form a cluster. And we thought from a Bayesian perspective, if the likelihood is invariant, maybe the prior can help us to sort of come up with an identifiable model. And this is what we have been pursuing in that context. We thought, okay, we want to use a prior which will enable us to come up with an identified model. And we want to sort of use the prior to distinguish between subcomponents which form together, which belong together and form a single cluster. And we also want to select the suitable number of clusters at the same time. And if you think about this, okay, on the upper level, we want to have a model-based clustering solution, and on the lower level, we want to have a semi-parametric approximation solution. And the priors we're specifying need to reflect this. They need to, on the upper level, support solutions which are good for model-based clustering. On the lower level, they need to strive at having a good semi-parametric density estimation. And in particular, if you think about the semi-parametric density estimation, there is some ambiguity on how you want to achieve that. If you think about a kernel density estimate, that's also just a mixture of normals, and you're just putting them next to each other, but they don't have much overlap. So we thought we want to have a different kind of density approximation on the lower, where sort of all of the subcomponents should share some characteristics. They should have means which are sort of overlapping. So we want to pull them together to a common cluster mean, and in that way ensure that subcomponents know that they belong together. So we've decided to pursue a very specific strategy for approximating the semi-parametric density estimation on the lower level, and in that way ensure that subcomponents would belong together. So for the upper level, on the cluster level, we can reuse what we have seen on, okay, we want to have a sparse prior on the component weights to allow for this automatic selection of the number of clusters. And on the lower level, on the upper level, we also don't want to shrink cluster means together, but they should be sort of as different as possible to allow to distinguish between clusters. And on the subcomponent level, we want to fill all of the components we have. So we put sort of the reverse to a sparse prior, put a prior which ensures all of the components are filled. We shrink the subcomponents together, and we also try to enlarge variance covariances a bit to have more overlap ensured. And this should give us dense and connected cluster densities. To show you how it worked in practice, we again used the simulation with artificial data. This kind of simulations with artificial data are in this mixture of mixtures context frequently used. So you assume the true model is a mixture of normals. So you have each of the colors is used for one of the normal components, but you would say you have 4 clusters, and the first cluster has just one normal component. The second has 2 normal components, the third 3, and the fourth has again 2 normal components. So you have in total 1, 3, 6, 8 normal components, but you want to come up with 4 clusters. So what we want to end up with is a 4 cluster solution on the upper level, and we want to use on the lower level mixtures of normals to approximate each of these distributions here. And for simplicity, we fixed the number of subcomponents on the lower level to 3. So even if the true would be just 1, we would be using 3 normal components. We would be trying to fill all of them, and we would then just have duplicate components. So adding more complexity than really necessary, but trying to have enough flexibility to capture non-Gaussian shapes on the lower level. And So this is the clustering we want to detect, and this is what the fitted distributions looked like. So we were really able to find these 4 different clusters. We were able to come up with an identified model and have on the upper level the number of filled clusters on the upper level. The mode estimate would have been 4, and we would come up with good approximations of the cluster distributions on the lower level. Good. So to sum up, and also some future work we're envisaging in that context, the ideas I wanted to show you that Bayesian estimation and thinking about good prior selections can help to solve or deal with unresolved issues in model-based clustering, things people have thought about, and the prior choice. And in particular, what we thought interesting is that the parametric families we're using for our priors are very, very standard. So we're not doing fancy extensions of the parametric distribution of the priors. We're just trying to give guidance on how to select the parameters of the distributions you would be using anyway. And often it's done rather not in a conscious way, but obviously these kind of decisions already have quite some impact on your results, in particular if you think about the weight distribution and the Dirichlet, which is something everyone's using. People have been thinking of having hierarchical structures for that to impose certain features in your posteriors, but obviously already thinking of how to choose carefully the single value has already a huge impact on the results, and it can help you to estimate the number of clusters or components for your mixture distribution. Shrinkage priors can help you to distinguish between cluster relevant and irrelevant variables, and these kind of things can happen sort of in one MCMC estimation. You don't need to do stochastic search and estimated different models. And what we were also thinking of is having a mixture of mixtures using the prior information to help us resolving this identifiability issue, which is in the likelihood. So it's really, if you think about the problems the likelihood has, adding the prior can help you to get a posterior which in the end is sort of better behaved. But you need to think about what prior choices do you need to make to come up with the solutions you're interested in. So what would be the next step? So if you think about the mixtures of normals, we haven't talked about the variance-covariance matrices so far. So that would be another step, thinking about good prior choices in that context, also to come up with, to induce parsimonious solutions. We could also think about mixture models with other component distributions. We're thinking of the latent class model, or looking at biclustering, co-clustering, things like that. If you think about what has been presented in this conference, there are a lot of different extensions of this basic mixture model possible. And the question is also, can further flexibility be gained if you relax some of the assumption you're doing in, for example, the choice of the symmetric priors, or also if you think about this independence assumption. Maybe the prior on the component weights should be linked to the distribution you're assuming a priori for your means, or things like that. Thank you very much for your attention.
Okay. So, thank you, Bettina, for this very interesting talks. A lot of aspects that can, for many reflections about this problem of estimations. So, if are questions from the floor, if any, there is one. Somebody can help you with the microphone. I will do that.
Thank you. Stick to my microphone. Shout.
Thank you very much for a very, very insightful, talk among all the subtleties of all these choices. It's clearly a lot of, you've summarized beautifully a lot of knowledge and experience. I really like this two-level mixture for there's many aspects to discuss, but that part, I was just wondering if you couldn't push it to the extreme in a way. Why do you need for your sub-component mixture? Why couldn't you assume the same mean? I think you might just simplify. You've said you will pull them together quite strongly. Still, it's another subtle choice between how you pull those, how you let the others. Have you considered just saying they have the same mean, and would you lose?
Yeah,
maybe not. You wouldn't lose, and maybe it's clearer somehow.
Yeah. So I think it depends on what. Still, in this prior specification, you induce certain cluster shapes you're able to approximate, and with all this pushing together, you're still getting very, very dense cluster distributions. And Gertrud was also playing around with changing this price setting, trying if you have a mixture of cell distributions which have this comet-like shape where you have a center, but then you have these long tails. And then you would need a sequence of components which have a lot less overlap. Then you would need to sort of, if you have this kind of shape in mind, you would need to include that also in the prior specification of the component distributions and how should they behave to belong together. So I think the easiest is like pushing them all together and then coming up with a solution where you have the centroid behavior, which sort of reflects also the cluster structure, which my feeling often is in application, this is a nice thing to have sort of a cluster which can be represented through a centroid, and we have several normal components. We're all pushing towards that centroid. But if you think you want to have something more also like asymmetric or skewed, and you need something like a very dense and less dense, then you would need to sort of change this prior setting there. But again, if you think about it and you explicitly state, I'm interested in clusters of that shape, then this would need to impact on how you specify your priors, and this will help in detecting the structure you're after.
Thank you. Unfortunately, time is over and the specialized sessions have been already delayed. So I would like to thank again Bettina. And
Thank you.
So, I think we can start. So I think we have not to delay anymore. And so, welcome to everybody, and thanks for attending this invited session on semi-parametric models and methods for hierarchical data. We have 3 talks and with different applications from educational context to healthcare context. And so I think we can start with the first speaker, who is Chiara Masci from Politecnico Milano. Chiara. Excuse me. Pointer.
Okay, so then I will stay here because I cannot find the pointer, sorry. Okay, good morning everyone. First of all, I would like to thank Anna Maria Paganoni for this invitation. So, my talk will be about bivariate semi-parametric mixed effects models for classifying the effects of Italian classes on multiple student achievements. This is a joint work together with Francesca Ieva, Tommaso Agasisti, and Anna Maria Paganoni, who are also from Politecnico di Milano. Here is the outline of the presentation in order to give you an idea of my talk. So I will start introducing and motivating our research question. Then I will enter in the merit of the methodology that will be about the development of bivariate semi-parametric mixed effects model. I will show a brief simulation study in order to give you an idea of how the algorithm performs. And then I will show the application of this model to the Invalsi educational data. So we present the Invalsi database and show the results that will be about the identification of subpopulations of classes. Okay, so let's start with the introduction. So the aim of this work is to develop an expectation maximization algorithm for bivariate semi-parametric mixed effects models for hierarchical data with the final aim of use it as a tool. So apply it to Invalsi data and use it as a tool to perform an unsupervised clustering of the Italian classes, standing on their different effects that have on both reading and mathematics student achievements. So in particular, the research questions that we want to address by means of this application is whether there are differences among the effects of Italian classes on their student achievements, then if it's possible in particular to identify subpopulations of classes that have different effects on reading and mathematics student achievements, and also if the class effects on these different subjects are related somehow. And in a second step, also if it's possible to characterize, identify subpopulations of classes in terms of classes characteristics of teacher practices. So let's start describing the model. In the scenario of mixed effects models, so the statistical literature, in the statistical literature we have, there are many models, mixed effects model that have both parametric assumptions on the fixed effects and on the random effects. So we have this kind of models both in the univariate and the multivariate setting, and also these models have been broadly applied in the educational literature. There are also some works in the direction of relaxing the parametric assumption on the fixed effects, but still maintaining parametric random effects. Our contribution will be in the direction of developing some models that have non-parametric random effects, so some mixed effects model with non-parametric random effects, but still parametric fixed effects. So in particular, by developing this kind of models, our aim is to find a model that induces a clustering structure at the highest level of the hierarchy of data, and also, since I will focus in particular on the multivariate setting of these methods, to model the correlation that we can have between multiple response variables. So, if we start considering a mixed effects linear model with two levels, the model takes this form. So we have the answer variable yi, that are the observations within group I, that is equal to a fixed part where the coefficients are the same for the entire population, plus a random effects where the coefficients are group specific. So in a parametric framework, usually the random coefficients C are assumed to be normal distributed with mean zero and a certain variance covariance matrix. But our work was in the direction of developing a semi-parametric framework in which C follows a discrete distribution with an unknown finite number of support points. So if we consider the special case of a model in which we have only one random intercept, one random covariate, and P fixed covariates, the model takes this form. So we have the fixed part that is still the same in the of the one of the parametric framework, while the random effects, in which we have the random intercept and the random slope, we have the coefficients that are not indexed by I anymore, where the I that goes from 1 to n are the number of groups in which data are nested, but they are indexed by L, where L goes from 1 to capital M, where capital M is the total number of support points of the discrete distribution of the coefficients. So in particular, the bivariate coefficients C0L and C1L assumes a discrete distribution that we can call P star that has capital M superpoints, where capital M is assumed smaller than n, where n is the total number of groups in which data are nested. And also the important thing is that capital M is unknown, so the algorithm is able to estimate the number of superpoints in which the data are clustered. Each group I then will be assigned to one of these cluster L that is characterized by this couple of parameters, and since capital M is less than n, we can consider it as an inbuilt clustering tool. So as I said before, in this special case, we are also considering the case in which we have multiple response variables. So if we then extend this model to the bivariate case, we have an answer variable that is bivariate, so the first and second response, and we have again the random intercept and the random slope. In this case, we have the bivariate random intercept, so the intercept related to the first and to the second response, and also the bivariate random slope, of course. While for the fixed effects, we still are linear parametric assumption with the answer variable, in which we have, again, the coefficients related to the first and to the second response. The important thing also that we can notice is that the number of subpopulations related to the first and to the second response are both unknown, and they are allowed to be different. So we can identify a different number of subpopulations related to the first or to the second response. CMK, that now are the random fx coefficients, assumes a discrete distribution, in this case with m times k superpoints, where, as I say, they are both unknown. And now each group I will be assigned to this bivariate cluster MK. Okay, when we estimate the maximum likelihood estimator hat P star of the distribution of the random coefficients can be actually expressed in this way. We have a set of points, C11, CMK, that belongs to R4 because we have the 2 random intercept and the 2 random slopes. And then we have a set of weights, W11 and WMK, that are all positives that sum up to 1, that represents the proportion of groups that belong to each bivariate cluster MK. The estimates of the number of subpopulations related to the first and second response to capital M and capital K, and also all the coefficients, the random and the fixed coefficients, are obtained by using an expectation maximization algorithm in which we maximize the likelihood function, where the likelihood function takes this form, and we call this algorithm as BSPM algorithm, bivariate semi-parametric EM algorithm. So we iterate the expectation maximization algorithm until the convergence, until a fixed threshold is reached. Okay, this algorithm is actually the multivariate extension of the one proposed in one of our previous work, in which we were considering the univariate case. Well, the improvements that, of course, it can handle multiple response variables. Then modeling the multiple response variable, we can also estimate the correlation among the subpopulations distribution related to the first and to the second response. And also the covariates are allowed to be group specific and also response specific. So in particular, since we are starting from n groups in which the data are nested and we will end up with the identification of subpopulations, during the expectation maximization algorithm we have to perform the support reduction. And this is done standing on 2 criteria. So the first one is that when 2 points of the discrete distribution are closer than a fixed threshold, that is a tuning parameter that we choose at the beginning and that we call D, if they are closer than this threshold D, they collapse to a unique point that will be obtained as the average of these 2 starting points, and the weights will sum up. The second criterion is that we can fix a minimum number of groups belonging to each cluster, so choosing as a threshold W tilde, and if a cluster contains less than this threshold, then it is deleted from the samples. Okay, so just to give you an idea of how the algorithm can work, I will show now a very brief simulation study. So we simulated n groups, so 100 groups of variables, in which we have the first here the first response and here the second one, in which we induce the presence of 3 different clusters for the first response and 2 different clusters for the second response. Here is the result of one of the 100 runs. Choosing d equal to 1 as threshold value, we see that the algorithm is able to identify the presence of 3 subpopulations related to the first response and 2 subpopulations related to the second one. So the algorithm identifies how many subpopulations we have related to each response, and also it can estimate the regression planes related to each of these subpopulations. Okay, one of the advantage, of course, of this algorithm is that it's also completely identifiable, in the sense that we can have 2 sources of correlation between the first and the second response. The first source of correlation is that we can have a structural correlation among the presence of the subpopulations. So we can have an association between the subpopulations related to the first and to the second response. The second source of correlation is the one that is catched by the errors. So if we simulate 4 different situations in which we induce a correlation, association among the clusters and not, and in the second case in which we induce dependence of the errors and independence, we can see that the algorithm is able to disentangle the effects of the correlations given to the subpopulation distribution and also to the errors. So, for example, in the case in which the errors are not independent, we see that the covariance of the errors is not 0, while when the errors are independent, then it's 0. And W is the matrix of the weights that tell us the distribution of the groups on the m times k identified clusters. And we see that if there is a structural correlation among the clusters, the distribution of the groups on these m times k support points is not uniform, but we have some clusters that collect more groups than others. While if we do not induce any structural correlation, the distribution of the groups are quite homogeneous among the clusters identified. Okay, so we decided to develop this kind of model because our final aim was to apply it to the Invalsi database as a tool to perform a clustering of the classes, Italian classes. So Invalsi is a national Italian institute for the educational evaluation of instruction and training, and it tests Italian students in different subjects, in particular also in reading and mathematics, and at different grades. So we have an information longitudinal data, because for each student we can track his performance across different years. Invalsi collects also information about students, classes, and schools by means of questionnaires and also tests. In our case, we will focus on 2 levels of the hierarchy in which the data are nested. In particular, at students level, we will consider both mathematics and reading Invalsi test score at grade 8, that is the last year of second junior high school, and the mathematics and reading Invalsi test score at grade 5, that is the last year of primary school. Moreover, we will take into consideration the socioeconomical index of the student, the gender, and also the immigrant status. The other level of the hierarchy that we consider are the classes. And about classes, we have information about the class body composition, so the percentage of females or males, immigrant students, the average socioeconomical index, for example, and also some new information of the year that we are considering, that is 2016-2017, that is about personal information of teachers and also teaching practices, so the way of teaching in the classes. Okay, our aim is to apply a bivariate semi-parametric 2-level model in which we consider the students, that is level 1, nested within classes, that is level 2, and we consider as output variable the student test score in mathematics and reading at the last year of junior secondary school, so Math 8 and Read 8. And we are interested in seeing how this association change, its association with the previous Invalsi test score, so at the last year of primary school, to see how this association, this correlation change across different classes, and in particular if it's possible to identify groups of classes in which this correlation change. We do that by adjusting for the socioeconomical index, gender, and immigrant status of the students. So we apply the BSPM algorithm by choosing 0.5 as a threshold distance for the collapsing of the masses. And we see that the algorithm is able to identify 5 different subpopulations of classes related to the effects in mathematics and 4 different subpopulations of classes related to the effects in reading. Here we can see the estimates of the fixed coefficients. For example, ESES has a positive coefficient, meaning that students that, on average, students that have higher socioeconomic index are associated to higher performance. Then the gender has, being females, has a negative effects in mathematics and a positive one in reading, for example, while related to so the weights are the proportion of classes belonging to each subpopulation. Here we have the estimates of the intercept and of the slope. It's easier to see the visualization of these results. So if we look at the 2D projection in which we have on the x-axis the random covariate, so previous test score of students, while on the y-axis we have the actual test scores of students. Here we have the 5 regression lines identified for mathematics and the 4 lines identified for reading. Each line, the width of the lines are proportional to the number of classes belonging to each subpopulation. We see that, for example, in mathematics, we identify 2 main subpopulations, the bigger ones, that collect the major part of the classes. And with respect to this reference subpopulation, we see that we have 2 subpopulations in which students, actually, we can interpret them as classes that have a slightly positive effect with respect to the reference, because given the same starting level of the student, the expected test score of the student is higher with respect to the reference subpopulations. On the opposite side, for example, this subpopulation, m equal to 4, are the subpopulations of classes that have the negative effect, because given indeed the previous test score of the students, its expected actual test score is very low with respect to the average. Regarding the reading results, we see that the reference subpopulation is actually the best one, so the main part of classes are in these subpopulations, and we have some classes that are in these 3 subpopulations that have a slightly negative effects with respect to the reference one, because the expected value of students in these classes is lower with respect to the reference. I don't know if I have, 3 minutes, okay. The point is that after the identification of these subpopulations, it's possible to identify if there are some class and teacher characteristics that are related to the presence of these subpopulations. So, yes, I will start with this. They were like backup slides. So we identify 4 different kind of subpopulations. So we have the reference subpopulations, so that are the subpopulations that contains the bigger part of classes. With respect to them, we want to see if there are differences in class characteristics between these reference subpopulations and the subpopulations in which we have both negative effects in reading and mathematics, and the ones in which we have opposite effects in reading and mathematics. So classes when we have positive effects in mathematics and negative one in readings, or vice versa. So we apply a lasso logic model in which we consider the belonging of each class to one of these clusters by varied clusters, and we consider all the class level characteristics as covariates, and we see that we can identify some class level characteristics that are actually associated with the presence of these subpopulations. For example, the classes where the contacts among math and reading teachers are very present are less likely to belong to the reference cluster, for example, or the elder is the teacher, both in math and reading, the less likely are classes to belong to the reference population, for example. We have also some kind of relationship with the kind of teaching method. So teachers were asked to answer questions about their teaching methods, their habits in class, and we have also some differences between these subpopulations identified. So I come back to this. Here we can also see the estimates of the metrics of the weights and also the variance-covariance metrics of the errors. We see that the distribution of classes on these 5 times 4 subpopulations identified is not uniform, so there is a kind of not independence between the subpopulations in reading and mathematics. And also the fact that the errors are also correlated, the errors related to the mathematics and reading, means that the portion of variability, in the portion of variability that we are not able to explain, there is still some association related to the first and to the second response. Okay, to conclude, I can say that the BSPM algorithm allows to identify the presence of subpopulation in the highest level of hierarchy when applied to classification problem where data have a nested structure, and that they can jointly model the cluster distribution related to the first and to the second response. When applied, of course, to the Invalsi data, is able to identify some class effects related to the reading and mathematics that are also associated among each other. And about the future work, an idea is also to extend this model to a 3-level model in which we insert also the school level, so in order to consider students nested within classes, nested within schools, in order to disentangle both the between schools and the within schools variability. And that's it. Thank you for the attention, and this is some references.
Thanks. Thanks, Chiara. There are questions or comments for Chiara?
Yeah, some guidelines for the threshold. How sensitive are the results to this choice of this?
Yeah, okay. You mean about the threshold distance D? Yeah, this is actually the tuning parameter that mostly affect, of course, the results of the algorithm. So we thought about a method that can be a guideline to choose the threshold D, that is like measuring the entropy of the matrix of the weights W. Because in the worst case, so when the algorithm is assigning each group, each class in our case, to a subpopulation, so for each class we have the distribution of the weights, so the probability of each class to belong to each subpopulation. In the worst case, we have a kind of uniform distribution of the probability. Why? In the best case is the one in which the algorithm assigns with probability 1 each class to a cluster and then probability 0 to the other ones. So in my opinion is that when the threshold, I mean, when you pick a threshold D that is the best one, I mean, for the order of the data, are in the case in which the entropy of the metric is minimum, because it means that the algorithm is actually assigning the clusters with a kind of high level of certainty, let's say. While when the entropy of the matrix is quite high, it means that maybe D is or too small, so maybe too sensitive to the presence of the subpopulations, or if D is too high, then it's collapsing everything. So it depends also on the like your aim, how many, for example, subpopulation, how much sensitive you want to be to the differences among the data. Yeah.
Okay, so thanks again.
Okay, thank you.
Move to the second speaker, Carla Ambigini from Florence University.
Okay.
And please.
Thank you very much. Hi everybody, I'm Carla Rampicchini from the University of Florence, and this is a joint work with Anna Gottard, Leonardo Grilli and Giulia Vannucci. And thanks, first of all, thanks a lot for inviting us to present this work here, and also to discuss a linear mixed model and 3 algorithms that are in line and close to the presentation of Mashi before. Okay, so we propose a method to exploit the ability of trees to predict response in mixed model. and also we reason on how to interpret the result coming from tree-based models. Okay, so this is because the class of predictive algorithm is nowadays very used in applied works, and sometimes there is a misinterpretation of these kind of models. So they are easy to interpret, but sometimes this interpretation is not so proper. So I try to explain quickly. Sometimes regression trees are applied not only to predict the response, that is a main proper use of these models, but also trying to explain why we obtain a given response, like in this paper here. And this is not a proper way to use these models. I try to explain this with a simple simulation example. Here we are trying to predict a response, a quantitative response, and we have 4 explanatory variables. Each of these variables is a normal variable, and if you use a tree to predict the response, it comes out that the main variable is x1, okay? While the other 3 variables do not enter the tree, but x4 in a part of the tree. The problem is that the data generation process of this data is that x1 generates x2, x3, and x4, and these are all linear models, simple linear models, so with the same parameter, while x5 is generated using the value of x2, x3, and x4. But if you apply a tree, the tree tries to predict the response, and the prediction is based mainly on the first variable without using x2, x3, and x4. This is correct for a tree. The important thing is not to interpret the tree as something that can also help you describe the mechanism which generates the response. So our proposal is to use the tree to increase the predictive power of a linear model, and while using a linear model to increase the interpretability of the tree. So, and we use this to extend the linear mixed model where the response is a continuous response y, and the units are, the observation are hierarchically ordered, like in the Invalsi data that Chiara presented before. And also our application is with Invalsi data, okay? So in this model, we have a linear part where we consider all the covariates, both at the level 1, say a pupil level, if you consider Invalsi data, and at level 2. So, for example, school characteristics, okay? And we have also a non-linear part that is represented by the tree, okay? Plus a random effect part. In our model here, the random effect is considered a normal variable, but is it obviously possible also to stay with other kind of distribution. So we call this a tree-embedded linear mixed model, but the important thing is that this model can exploit the ability of the tree to consider nonlinear effects and also interaction, and have a mixed model that is more flexible in this way. So this tree-embedded linear mixed model is the mixed effect version of a proposal of Vannucci and Gothard called semi-linear regression trees, and these models are very useful when we want to insert quasi-linear dependencies in our models, and they have a good predictive performance and also providing, explaining and understanding on the mechanism of generate the response. In particular, to estimate this model, we exploit a two-stage procedure based on backfitting that alternates the estimate of the linear and random effect part using GLS and the tree part using CART until convergence. I will show you the algorithm we implemented in R. So starting from the data have a hierarchical structure with, say, pupils within schools, and we have covariates both at pupil level, say the X covariates, and covariates at school level. For example, the kind of school, public versus private, or things like this. And we start in the initialization step, the tree is initialized at depth 0, and then we repeat iterating from the tree-based residuals, estimate the tree, estimate the fixed part, and so on, back and forth until convergence. And at the end, the first step is an estimation where the parameters of the model are estimated all together. So the algorithm is very fast and works very well. And now I will show you an application of this model to Invalsi data. So thanks to Chiara to present the Invalsi data, and the problem we present is quite similar to yours. We consider the math test of a cohort of students considering the test taken at the 5th grade at the end of the elementary school and the test taken at the end of level 1 secondary school, the 8th grades, okay? So the data set is obtained merging these two occasions of the Invalsi test, and it turns out that we have a huge data set, and our second level is the school. So we have pupils embedded in school. The total number of schools is 5,070, and the average number of tested students per school is about 100, okay, with a standard deviation of 54. So our aim is to predict the math equivalent of such talents, having some clues on understanding why we observe such difference in the results. So we consider a lot of variables, a lot of covariates. I just listed here the ones who comes out to be significant in explaining the response. And in particular, the main covariate is the same you used, so is the value of the test at the end of elementary school, plus the socioeconomic status, the gender, if the student has or not a regular career, and the citizenships. So if he's immigrant of first generation, of second generation, or Italian. And we consider also a lot of covariates at level 2, at school level, in particular the geographical area, divided in 5 areas. If the school is located in a big town, in a provincial capital, the average size of the classes of the school and the number of classes in each school, and also if the school is public or private. Moreover, we considered the cluster means of the individual or the pupil level covariates. So for example, the proportion of immigrants in the school, the average value of Math 5 in the school, and so on. So looking at the data, this plot is just a descriptive plot describing the relationship between the score at the 5th grade and the score at the 8th grade. And the different colors and lines refers to the different areas where the schools are located. You can see that the relationship between these two tests is quite different depending on the school is at the south, center, or north of Italy, okay? And so we hope to obtain a model that take into account this different pattern of the relationship. Okay, so we estimate many models. First of all, we estimate the standard linear mixed model. Then we estimate the standard linear mixed model plus the cluster means of the individual covariates. And then we estimated the tree embedded mixed model in many ways, with and without cluster means. And also we try a longer tree and so on. For this example, we will stay with the tree-embedded mixed model with a short tree just to see how it works. Okay, as you can see, this model is the blue one and is a nice model with 22 parameters. And this is the tree part of the model. And as you can see, the only two variables that enter the tree are the score at the end of elementary school and the area. So among all the covariates considered in the model, only these two covariates enter the tree. If we consider a longer tree, no new covariate enters the tree, just it split more the group, okay? The number inside the nodes are the percentage of pupil with that node, okay? If we consider the final mixed model, I remember you that in the final step of the estimation, the model contains both the linear part and the tree part of the model. And as you can see, all the variables, obviously in this final model, all the variables are significant. And in particular, for the tree nodes, you can see that the score increase on average of about, for example, of about 5 points for pupils who have a low value of Mat 5 and stay in the south. Okay, this is quite counterintuitive results that is difficult to find out with a simple linear mixed model without a tree. So the tree helps in this way. And this is just to show you, this is a plot representing the relationship between the score in math at the elementary school and at the end of the 8th grade. That the gray plane refers to south, while the green plane refers to north. And as you can see, the function is a step function. Okay, so here is evident the effect of the area on the relationship between these two scores in south. Okay, this is another plot. This plot is the so-called caterpillar plot. It represents the estimated random effect of the school for each school coming from our model, and the red lines refers to the north part of Italy, while the blue lines refers to the south part of Italy. And as you can see, the northern school concentrate in the middle of these caterpillar plots. That means that the cluster effect, the school effect in the northern part of Italy is similar to the average, that is 0, while for the south part of Italy we have the more extremes, so schools that are very good and schools that are very bad, okay? So there is a greater variability in the contribution of the school in the south of Italy than in the north of Italy. So in essence, this is the interpretation of this caterpillar plot. And also we are reasoning on how to validate and predict from our model. Since the model is estimated on hierarchical data, the validation and prediction procedure must take into account this hierarchy on the data. So in partitioning the whole data set in, say, 2 data sets for the training and for the test, we have to decide what kind of prediction we are interested in. For example, if you are interested in predict the result for a pupil in a given school, you have to sample pupils from each school. While if you are interested in predict the results for a pupil in a new school, you have to sample schools and all the pupils embedded in this school. So this is important because we cannot use automatically, for example, what you can have from tree partition algorithm. You have to write down your own software to perform this way. Otherwise, the conclusion you reach are not correct because you are not taking into account the hierarchy on the data. So we made this validation and prediction 2 times. One, sampling at pupil level, the first 2 columns refers to this, while in the second step we try to predict for a pupil in a new school, sampling from school, dividing the data set using schools. And as we can see from this table, at pupil level, our proposed model outperforms also random forest in a predictive sense, because random forests that are very, very performant to predict, but they ignore the hierarchy. While at the school level, random forest outperforms other approaches, but the problem is that with random forest we cannot explain anything. So if we want to exploit both the predictive power of a model and also have some interpretation on why we have these results, a mixed model is better for this. So conclusion, and so we try to extend random effect regression trees, proposing a tree-embedded mixed effect model with both a tree component and a linear component, thus increasing the flexibility and also the predictive ability of the model. So because we handle simultaneously linear and nonlinear association, and also we exploit the covariates at all levels, the pupil level and the school level. And also we increase interpretability of the tree, because our models have good predictive performance while providing insights for explaining and understanding what's going on. We have a lot of work to do, because this is just a first work. In particular, we have to study and implement cross-validation for hierarchical data to take it properly into account the hierarchy of the data, and also to evaluate the performance of the proposed procedure throughout a simulation study. And moreover, we would like to extend this, but this is easier, using random slope models and other types of response, such binary or ordinal. So thanks a lot for your attention, and here comes some reference.
Thanks. Very, very interesting. Any question or comment?
So as you have a linear part and a tree part in your model, do you have some variable selection mechanism behind?
You have, sorry, I have understood.
So do you have any variable selection mechanism in this model, because, or are you allowing for all the variables x and z in your tree part? And the second part of the question is it identifiable in each case? Because if you split in a binary variable, maybe in the tree, it's the same as you have a linear effect. So did you think about it?
I'm not sure to have well understood your question, because I cannot hear very well. Anyway, the variables that are in the linear part are the same variables that there are in the tree part. Is this the first question? And the variables are both at level 1, say gender of the pupil, and at level 2, say school is public or private. No problem with the scale of the variable, continuous or ordinal or whatever, because this is just a regression model, so you can use any kind of variable. The response is continuous, is the test score. I don't know if... Okay. You want to know how we represent, say, the area, south, okay? So here, the number inside the nodes of this tree are the values of the parameters that appear in this model. That's this mu in the tree part. Can you see the parameter mu in the tree part? Okay, when you have, say, south is a categorical variable. So it's coded 1 for school at south and 0 for school that are at north, say, okay? So when you estimate this model and you have to insert this node here, the last one on the right, we set to 0 the parameter for south and to 0 the parameter for north, and the model estimate 5.37 for south. So it's like I have a dummy variable. So these I here in the model are indicator variables. So each node is represented in the final model as a dummy variable, taking on value 1 if you are in the node and 0 otherwise. I don't know if it is clear enough. Yeah. But this is an interaction model, because here is not only to be in south, the last node on the right is not only to be in south, but is also have a math score greater than 31, so it's not the same. It's an interaction effect.
Yes,
while math is a continuous variable.
Yes.
Yeah.
Okay, thanks again. You have to go to the third speaker. Thanks again.
Thanks to you.
Where is it? Okay, this one. So the third speaker is Linda Sharpest from London University of Hygiene and Tropical School. Very difficult. Please, Linda.
Okay, thank you very much. Thank you, Anna, for inviting me to the conference. It's been hugely enjoyable and interesting, so thank you. And thank you for still being here. I really do appreciate that. I'm going to talk about something a little bit different, and that's clinical trials, and in particular, how we might improve trials that try and prevent the onset of some new disease in the future. And this is work with clinical trials people in Leeds, particularly my PhD student Isabel Smith. So clinical trials have been really effective in demonstrating cause and effect between treatments and outcomes, and they've had a large impact in medical practice. And that since that first trial in the modern era of medicines, they've been extended to other treatments, including prevention trials. But they tend to have this very simple two-parallel group design. And they can be limited. It's very difficult to recruit patients and to keep them in the trial. An average trial these days will cost about €2 million at phase 3, so they're expensive in time and money. And there's a big drive towards having more efficient trials. So when we design them, we have to make quite a few decisions, with the key ones being which patients do we study? Do we randomize patients or some kind of clustering of people? How long do we follow them to, and when do we make assessments, at what time points? Who makes the assessments, specialists or more general people? And how do we assess the onset of new diseases? And all those feed into the analysis. So the focus of today's presentation, although we want within this project to look at all those aspects, today I'm just going to talk about the classification scale and the analysis, and how we might make more efficient statistical more efficient designs and analysis just by changing the statistical methods we used. And I want to do this all through an example, so to make it more real to you, and that's the example of trying to prevent pressure ulcers. So pressure ulcer prevention trials usually take this kind of structure. So there are about 14 different areas of the body that come into contact with beds and so can be at risk of having a pressure ulcer. And they're assessed, the skin at those sites is assessed at baseline and then at a number of follow-up times beyond there. So typically each patient would contribute maybe 50 to 120 measurements throughout the trial. But the common primary outcome measure is just to take a single measure, so say the incidence of a pressure ulcer at any time, or the time to the first pressure ulcer of a particular severity. So pressure ulcers are measured using a semi-quantitative ordered scale from healthy skin to very extensive pressure ulcers. And a category 2 pressure ulcer is usually taken as the outcome, the thing that we want to measure. And the way we measure, although we've got this underlying continuous process, the way we assess it is by taking snapshots of the skin at particular times. So we've got interval censored data, and we can miss movement between different stages of development, between measurements, and we may miss going through stages completely. So we can overestimate the time it takes to develop a pressure ulcer or as I say, miss it. So for that kind of data where we've got this categorical, ordinal categorical stages and interval censoring is naturally falls into a multi-state model. And so what we want to do is consider this longitudinal data for each patient. So we're focusing on how the data are generated rather than aggregating the data in some way to fit a chosen statistical method. And today I'm just going to concentrate on patient level data, so not each individual skin site. So multi-state models are very well established. They're even older than I am, so we know how to deal with them. And if we look at a continuous time measure process, then it's defined via instantaneous transition rates or transition intensities, and that's the instantaneous probability of moving between states at any time. We can make those transition intensities dependent on covariates, and the key one for clinical trials is the treatment allocation, and we would have that treatment effect on each of the different transitions. The likelihood is defined using the probability of moving between two states in a particular time interval, and those probabilities would be fairly complicated non-linear functions of the transition intensities. So if we have measurements for a particular patient at times t to tni, so x are the measurements of those patients, then we can write down the probability of movement between the observed states within the observed intervals. And we have a product across each individual person's transitions, and then the full likelihood is across all individuals. So the really bad news is that that likelihood is very complicated and we can never write it in closed form. And if we can't make these methods accessible to clinical trials units, we may just as well talk to the cat, because nobody would actually use them. So it's a difficult situation. But the good news is that there are some well-established numerical algorithms to maximize the likelihood. In particular, we use a package called MSM, which was developed by Chris Jackson, and that will give us maximum likelihood estimates, assuming Markov models or piecewise continuous Markov models. There are other packages available in R, SAS, and Stata, so we can make them accessible to the clinical trials units. But there are a few packages that really deal with the interval censoring as efficiently and easily as MSM. And the other really important thing is the documentation for it is really good. And that's something I think we should concentrate more on. So today I'm going to compare the simple approaches that people take, incidence and time, to a category 2 pressure ulcer, and compare that to a multi-state model approach, and concentrating on the multiple assessments over time, how treatments affect different parts of that pressure ulcer development. And I'm going to do that through looking at a particular trial that's been completed called Pressure 2. Okay, so I'll just spend a bit of time describing Pressure 2. It had 1,800 patients who were at high risk of pressure ulcers, but didn't have a category 2 pressure ulcer at randomization. They all had at least one post-randomization follow-up, and there were a total of almost 10,000 patient assessments and 8,000 transitions. It compared 2 different matrices. Foam mattress was the control, and a more whizzy mattress was the treatment. And people were assessed twice weekly for the first 30 days and then once weekly up to 60 days or until discharge. At baseline, patients were in a mixture of different categories. 17% had healthy skin, 71% showed some alterations, and 12% had an early category 1 pressure ulcer. So the first option, the simplest option, would just to say, what's the incidence of a category 2 pressure ulcer? And the new matrices decreased that from 8.6% to 5.7%, giving us an odds ratio of 0.65. So quite a nice reduction, which was statistically significant. So although this very common estimand, the measurement of interest, is an odds ratio, we could just as easily have used a risk ratio, which is very similar because it's a rare outcome. Or a more interpretable estimand might be the risk difference, and there was a change of about 3% between the 2 matrices. But the incidence doesn't take into account at what time point the pressure ulcers developed. So what was used in the clinical trial when it was first, as a primary analysis, was the time to the first category 2 pressure ulcer. And they used a Cox proportional hazard model. So a hazard ratio of 0.69 was estimated, and again, it was pleasingly significant. But you can see from the Kaplan-Meier curve that this is the proportional hazards assumption is violated. So you can see there's a delayed treatment effect, no treatment in the first 7 days, and then a treatment effect starts to emerge. And that's very common in prevention trials, where it takes time for the important event to accrue. So we may have used a different analysis, and a common one is the mean survival time up to a particular time point, so the area under this Kaplan-Meier curve. And that was a difference of about 1.7 days in the time being free of a category 2 pressure ulcer over the 60-day period. And disappointingly for the clinicians, that's not quite significant, but it does, it at least doesn't make an assumption that's not valid. So if we have a look at a multi-state model description of this process, I've chosen this progression model where you have 4 states from healthy due to altered skin, then to category 1, and then category 2 or above as an absorbing state. And I've chosen a progression model, so that means what each state reflects is the highest category observed up to that time point. And we make the transition rates depend on the time from entry to the study, that's from randomization in a trial, and the covariate, the main one being the mattress that was allocated to the patient. So we can get lots of different information from this, but what we get first is the relative transition intensities at those 3 different transitions. And we can see that actually the new matrices have very little effect on moving out from healthy skin to altered. A little bit of an effect possibly going from altered to category 1, but going from category 1 to category 2, it has a really major effect. So we can see that this the effect, the mechanism by which the matrices are working are mainly on this transition from category 1 to category 2. So if we want to do a new trial, we should maybe focus on people who have got at least altered skin and possibly category 1. And we can download or get out additional output from this kind of model, like what proportion of the patients are in each of the different states over time, or what are the baseline rates of movement between the different states. So overall, the models basically say the same thing, I think, but some are more interpretable than others, and I like the multi-state model because of its greater information about the mechanism of action of the new treatment. So we wanted to go a bit further and say, what would be the impact of using multi-state models on the power of a new study? So we set up a simulation study which very much reflected the case of pressure 2. So we had equal allocation to treatment and control, moderate treatment effect across all of the transitions, very similar transition rates, very similar baseline categories, and we looked at daily assessments for a maximum of 60 days with a 5% rate of leaving the system due to discharge. We used 1,000 data sets for each scenario that we looked at, and we varied the sample size, length of follow-up, the interval between assessments, different baseline transition intensities for the control group. And we looked only at 2 treatment effects so far. One is the null effect, where there's no treatment effect at all, and the other was this base case effect, where it's 0.67. So there are some decisions to be made, and the first one is, what's the estimand of interest? So with the traditional models, it's quite easy. It's either an odds ratio or a hazard ratio, depending which you choose. For a multi-state model, we've now got 3 different possible treatment effects. So how do we deal with that in a clinical trial situation? We could use a completely unconstrained model and say, okay, we've got 3 treatment effects, or we could constrain them all to be the same, or we could do something in between. Okay, so given we've got those different estimands, how do we say whether this is going to be significant or not? So again, the traditional models have we could use the Wald statistics which is directly linked to the odds ratio or the hazard ratio. And if we use a multi-state model where it's completely constrained, so we only have a single treatment effect, again, we can use a Wald statistic for that treatment effect parameter. But if we've got unconstrained or partially constrained models, then we've got a difficulty with multiple testing. So we used a Holmes multiple test procedure, which is just a generalized one for only test, really. So for example, if we've got the completely unconstrained model with 3 treatment effects, we conclude that it's significant at a 5% level, if all 3 are significant at the 5% level, or if 2 are significant at a 2.5% model, or if 1's significant at a 1.67% model. And this plot shows the results of both the null and the base case models. So if you look at the 5% model, that's not the power, that's the type 1 error. So that dashed line along the bottom shows that the type 1 error is working very well for all of the different models. It's at 5%, so that's reassuring. So the other models show the base case situation, and throughout these, the purple line, this is tricky. So the purple line at the bottom is the binary outcome. The blue line just above that is the time to event outcome, the Cox model, and the others are different versions of multi-state models. And you can see the multi-state models always perform better in that situation. And in particular, if you look at is it a yellow model right at the top, that's the constrained model, we can get 90% power with about 500 patients, whereas for the traditional models, we need about 1,000 patients to get 90% power. And we can see that if we vary the length of follow-up, we get approximately the same power with 30 days follow-up from a multi-state model as we would get from 60 days follow-up for the traditional models. And similarly, it makes less difference, but change in the interval between measurements makes a little bit less difference, but we could increase that interval to 2 to 3 days using a multi-state model compared with daily for the traditional models. And just some general messages about the baseline, changes in the baseline rates. The multi-state models were always more powerful than a logistic regression, a binary outcome. And they had similar power to a Cox model, providing that the transition between category 1 and category 2 was quite high and previous events were quite low, because the two things would be almost the same. Multi-state model had a greatest improvement in power if the later transition rates were low, because with the other models we would not really observe many events. And if it's quite difficult to get from the healthy skin to altered skin, then they all have pretty bad power, which is possibly what you might expect. So what I would say about these models is that they provide much richer data from the clinical trial, and at the very least we should use them in sensitivity analyses to get an understanding of the natural history of pressure ulcers and how treatment interrupts that natural history. If we're prepared to use them when we're designing clinical trials, then we can increase the power based on these serial measurements. And we can do these simulations and use previous data to say which are the most efficient populations and what's the optimal frequency and length of follow-up. Now, this is just part one of this study. So part two, we want to look at multiple skin sites per patient, so we can introduce some random effects. And that's not straightforward because they're not necessarily exchangeable. We want to look at the effect of using less expert assessors who may introduce some misclassification, but perhaps we can balance that with using them more frequently than the experts who have to come in specially. And we want to look at accommodating missing data. So thank you very much for your attention, and there's some acknowledgements. Thank you.
Thanks. Linda, there is questions or comments, curiosity? I have just a curiosity, a non-statistical curiosity. Do you have a strategy to convince or to communicate to the clinicians the fact that it's more efficient, more complex models are multi-state?
I think the power argument is extremely convincing to them, because I think it's about 50% of trials overrun. You know, they overrun, or at least they can't get enough patients to satisfy the power. So if we can improve the power and make them more efficient, I think, yeah, that's my strategy anyway. Yeah, sorry. Do you want to?
Were you assuming that it was the same effort? You know, I mean, the power is very convincing, but were you assuming that, you know, running the trial, you had the same effort in would that be more effort in collecting that data, more expensive or whatever? Are you balancing any of that, or is that a question people could ask you, you know, because clearly it's always better to get more out of your data, but is the kind of cost of getting that data the same? Could people just say, well, it's more complicated to run, and how would you argue sort of against that?
I'm not sure it would be more complicated, because they have to monitor people, or otherwise, if that interval censoring stretches out too much, you would miss lots of important information. So they already would, they collect the data anyway, or they collect a reasonable amount. And one thing I think related to that is I think they should do more simulation before they start the trial to try and hone down some of these particular parameters. But yeah, thank you.
So I would like to thank again all of you and have free speakers. Thanks, and now I think it's lunchtime.
Yeah.
Thanks.
Thank you. Shall I just delete that? Shall I just? No, I'll leave it. Is that okay? Was I in time? I was in time.
I saw, yes, that's good. I think that the museum is something simple seems good. And it's on the way, in a way, from between here and town.
The museum is
Yeah, I saw it
in the
on
way
the map.
on the Abbey, but it's 200 meters you go on the Abbey.
Yeah, I saw it. It's just there.
Yeah, just on
Just
there.
there. Yeah. It seems really. I think it's good. Yeah.
Yes,
I
I think
tried
it's
that.
okay.
It's
And then if you have time, also Terme Baroniane, it's also only for walking. It's
okay.
park.
Yes, I would like to go to a park. Yeah. Because we've been much indoors. I think good. Outside is good. Thank you very much. Oh, good. Yeah. It's nice to combine all the
aspetto qua io.
I'm sorry that you didn't understand.
C'è la base qua.
Sì, sì. Voglio prima caricarla sulla pedina.
Giulia, vai tranquilla.
Vado, rimanete.
Io, vai
Se avete bisogno mi chiamate?
Sì, vai.
Vuoi darmi il piatto?
Bravissimo.
Non ti preoccupare. No, poi dopo mi muori.
No, no, non muoio. Dai che vado io. Chiamate se vi serve qualcosa, mangia. Vai. Prof, lei ha mangiato?
No, ma andiamo a mangiare adesso.
Ok, dai, adesso andiamo di là.
Quindi mo la mettiamo là, aspetta però devo mettere pure un'altra cosa perché poi dopo devo... No, abbiamo un'altra ancora.
Il pomeriggio?
Sì. No, sì, ma fra un'ora.
Sì, no.
Ok.
Devo fermare la registrazione però, se no...
Sì. Però possiamo...
Vi lascio acceso.
Ah, on regarde le sol avec le... Le prochain président de l'université, il y aura une photo de moi par terre sur le sol.
Grazie. Mettiamo Pure lo slide.